Okay, your new booklet is on collisions, explosions, and impulse. I wouldn't get too excited, it's not the same explosions as chemistry, although they do use the same physics principles, but there's not going to be any sort of exploding bombs or anything like that in this class. So, we're going to come across a couple of new equations, and we're going to use some of our old equations to be able to answer some of these questions. So we are again building on National 5 things and expanding on them. So in a collision, there are two factors that might affect the amount of damage which occurs to the vehicles involved. And this one is relatively sort of intuitive. It obviously has faster going, so velocity. And of course, how big they are to the mass. So those two things affect how much damage something might gain if it's in a crash. And momentum is a thing that takes these into account. Okay, so momentum is a measure of the amount of motion of an object and is defined as momentum equals mass times velocity, where momentum is P, momentum, and the units of momentum are kilogram meters per second. Obviously, M is for mass in kilograms, and V is for velocity in the usual meters per second. Okay, and because velocity is in the equation to work out momentum, momentum is also a vector quantity. So the direction of the momentum is the same as that of the direction of the velocity. And an object can have a large momentum because either it's got a large mass or it's got a large velocity. So there's two examples there. One is an oil tanker which has a large mass, so it's got a large momentum. And one's a shell air bullet, and it's got a large momentum because it's got a large velocity. And just a reminder about your kinetic energy equation. Any moving object has kinetic energy or moving energy. So kinetic energy is half mv squared, and it's a scalar quantity. An object has kinetic energy because it's moving, and the direction just makes no difference to the magnitude of that energy. So, example 1, nice and straightforward. A 2 kilogram ball moving at 4 meters per second hits a wall and rebounds at 3 meters per second as shown. Okay, so what have we got? This is it traveling at 4 meters per second, and this is it coming back at 3 meters per second. It wants to know the momentum after the collision with the wall, so we're looking at sort of this side first of all. So part A, momentum is mass times velocity. So the ball is 2 kilograms, and again, you're going to have to watch your signs this time, because if we say the original direction is positive, then it's going to be 2 times minus 3. So minus 6 kilogram meters per second. So it's probably best to write a little sentence saying the momentum, I'm just going to shorthand it to momentum, is 6 kilogram meters per second to the left, because we chose the right to be our positive direction, and it's a negative momentum. And B, calculate the kinetic energy before the collision with the wall. So this one I'm sure you can do yourselves without me helping you. But the kinetic energy is half mv squared so half times the mass, which is 2, times by the speed beforehand, which is 4. So half times 2 times 4 squared, which should come to 16 joules. Those ones are relatively straightforward, and the first questions in the question booklet are on those. But before I let go of the question booklet, I'm going to put you through one application of momentum. So, collisions use momentum, and we can find out what's happening before or after if we know some parts of the movement before or after. So, we normally do an experiment here, where we have the linear air track, where we have two trolleys on and two light gates. And what we do is compare the total momentum before the collision and the total momentum after the collision. And we also find the total kinetic energy before the collision and afterwards. So obviously, to find the total momentum before the collision, we need to know the mass of the trolleys and the initial velocities of the trolleys. And to find the momentum after, we need to know the mass of the trolleys again and their final velocities. So remember, momentum is mass times velocity. And then we'll compare those. And obviously, to find the kinetic energy before and after, we need to know the mass and the velocity before, and the masses and the velocity after. Okay, so linear air track is usually made of this because it's friction compensated, so it gets rid of most of the friction. And the mass is measured using the top hand balance. Vehicle A is projected through light gate 1. It collides with vehicle B, which is originally stationary, and both vehicles move as one through light gate 2. So basically they stick together and they carry on moving. So the timer calculates the velocities using the normal thing, so it's the velocity is the length of the interrupt time divided by the time on the timer. And the momentum of the vehicles before and after the collision are calculated. And the kinetic energy of the vehicles before and after the collision are also calculated. So the calculations you would use are this. So the total momentum before the collision will be momentum of trolley or cart A plus the momentum of cart B. So mass times the initial velocity of cart A plus mass times the initial velocity of cart B. And then afterwards, because they stick together, you can say the mass, they are now moving as one. So momentum afterwards is mass times velocity, but that combined mass times by the velocity that they're moving off at. You can, of course, treat them separately again, you would still get the same answer. And to find the total kinetic energy before the collision, you would do half mu squared, so half times mass times the initial speed squared for both of the trolleys. And then afterwards, because they move off as one, you can use them, you can look at them as one singular thing, so you'd add both of the masses together and do half times the total mass of both of them times by the speed of both of them squared. And again, you could take them separately and add them together and you still get the same answer as that. So, conclusions. Instead of me writing this because my pen is not very good at the moment, I'll let you write this down. So, these are really important. This is a really important conclusion. So, conclusion. So, in the absence of external forces, that's an important line, in an inelastic collision, momentum is conserved. So what we would do if we did this experiment, if we find the momentum before is equal to the momentum afterwards. But we find that the kinetic energy is not conserved. So in this interaction, kinetic energy is smaller afterwards. So the kinetic energy is not conserved. So the two equations, so mass of A times initial speed of A plus mass of B times initial speed of B is always equal to mass of A times the final speed of A plus mass of B times the final speed of B. But kinetic energy before does not equal kinetic energy afterwards. So I'm going to leave that up for a couple of minutes because I'm sure you will take a little bit of time to copy that up. And we'll move on and we'll do an example of these. Okay, if you need any more time, please ask the teacher to pause the video, but we are going to move on. So, got an example. A car travelling at 20 metres per second east crashes into the back of a stationary vehicle of mass 800 kilograms and locks onto it. An analysis of the accident shows that the speed of the wreckage immediately after the collision is 12 metres per second. So what's happening there is we've got one car stationary, one car moving at 20 metres per second. The 20 metres per second one crashes into the back of the one that's stationary, and then they both move off together. They're sort of like tied together. They both move off together at 12 metres per second. So, first of all, calculate the mass of the moving car. So we've got the mass of the second car, and we've got the initial speeds of both cars, and then we've got, again, afterwards we've got the mass of the second car and the speed of both of them moving off. So to find this, we have to use the conservation of linear momentum. So remember we said that we've got mass of A plus initial speed of A plus mass of B times the initial speed of B equals the mass of A times the final speed of A plus the mass of B times the final speed of B. So what do we know? What can we put into here? So the mass of A we don't know, so we still got ma times my initial speed of A, which is 20, plus mass of B, 800, times my initial speed of B, which is 0. So that's going to be 0 eventually, but we'll write it in anyway. Equals, afterwards, mass of A, we still don't know what mass of A is, but we do know it moves off at 12 metres per second. And I'm going to treat them separately. So mass of B is 800, and it's also moving off at 12 metres per second. Okay, so what do we have? We have 20 ma plus 0 equals 12 ma plus 800 times 12, which is 9,600. Gather all our ma's on one side, just like you would with algebra if they were x's. So 20 minus 12 is 8 ma equals 9,600. So ma is going to be 9,600 divided by 8. So ma is going to be 1,200 kilograms. Okay, so just using your conservation of linear momentum, you write down the equation first, put everything you know into it, and then it'll be a case of algebra and manipulating the numbers to get to the correct answer. And part B asks you to prove the collision is inelastic. So we know that if it's inelastic, the kinetic energy before will not equal the kinetic energy afterwards. So before the collision, we've got the kinetic energy is half times the mass times the initial speed squared of A plus half times the mass times the initial speed squared of B. So work that out. I'm sure you can do that without my help, but I'll just write it down slowly. So the mass of A we now know is 1,200. So half times 1,200 times by the initial speed of A, which was 20 squared, plus the half times mass of B, which was 800, times by 0 squared, which is 0. So we've just got half times 1,200 times 20 squared. So that comes to 240,000 joules. And after the collision, we can treat them both as one. So kinetic energy is half times the mass of both of them. So 1,200 plus 800. Times by the speed that they both move off at, which is 12 squared. So half times 1,200 plus 800 times 12 squared comes to 144,000 joules. So it's proving that it's inelastic, so we have to write a statement at the end to say the kinetic energy before does not equal the kinetic energy after. So therefore, the collision is inelastic. I'm going to send you some questions to practice on these kind of things. As always, I will be available on Teams if you want to ask me any questions, send me any photos of your working to see where you've gone wrong.